Hello and welcome. Right now we're going to look at what AI accelerators actually are. So we'll try to find out what purpose they have in this AI space by comparing them to how CPUs and GPUs work. We'll also look at some of the limitations as well. Right. So CPUs, as shown here, are central processing units which mainly specialize in proper logical operations. So you have a lot of bigger operations or bigger computations that can be handled by these CPUs. Right, and GPUs here are smaller but faster parallel processing units, which cannot do as complex operations as CPUs, but they can carry out parallel operations in a bit more efficient manner. And AI accelerators are a bit more specific use case oriented, and CPUs are a lot more general purpose oriented. And GPUs are more of specific purpose. They can perform mathematical computations a bit more faster than these all-in-one units because they have, like I said, they have more cores on average. And AI accelerators have the highest number of figurative cores, but they're actually called processing elements. So processing elements are just the cores in an AI accelerator. So the number of elements in an accelerator are the highest when compared to these two. And that's because they only do smaller subsets of these computations, and they mainly perform operations which are matrices and accumulators or accumulations. So these are all very raw, lower level mathematical operations that these AI accelerators excel in. And considering that in AI workloads, the highest importance is given to hardware that can perform matrix operations, even in convolutions and accumulations as well, they are given the higher amount of preference. When you look at it in a different way, if you have an entire bus and you have 15 people to transport, and assuming that the seating capacity of the bus is 15, then we can say that the bus is very efficient, right? Thing about AI operations is that AI operations are mostly dynamic. So they're not always going to have 15 people, right? So they're going to have, let's say, 3 people sometimes, or even 2 people sometimes. So the main objective of using or implementing an AI accelerator or just building one from scratch is that instead of using a bus which can handle 15 people to transport 3 people or even 2 people, we design a certain module that can incorporate these 3 people without wasting the remaining 12 slots in a bus. If we relate it to a CPU can handle a lot of processes, but then it can do a lot more than what we use it for in AI operations, right? And GPUs, they're a bit more AI oriented, but not strictly enough, because they can also do other operations as well, just like 3D rendering or even graphical processing and such, right? But AI accelerators, they are very strict and limited, but they're very power efficient and specific in their use case. So a CPU can be considered to be, let's say, a very intelligent person, right? Let's say it's just 3 or 4 intelligent people, and they can do a certain task pretty well. But if you consider a GPU is more like 5,000 or 10,000 average intelligence people. So they can do a task faster because they can break it down into smaller parts, and they can do simpler tasks faster. AI accelerators are pretty much related to GPUs in a very specific use case, but overall they can be considered to be, let's say, a factory line or an assembly line of workers who have no thought of free expression. So they have processing elements which are all chained together in a certain sequence. It can be directed whichever way you want, and these let's say these elements handle each part of the computation, and it flows strictly in a certain direction that we specify it. So this accelerator is very strict in a sense that it forms the exact operation that we give it without any room for versatility. So that's why accelerators are very simple, and they can perform the tasks in a very power efficient and resource efficient manner, because the GPUs can perform a lot of tasks, and they are more general purpose considered compared to the accelerators. CPUs are even more general purpose, but they're slower in workloads which need a lot of parallel processing. So that's why we need AI accelerators, because When we consider edge implementations like mobile phones, we can implement bigger models easily. But the problem with that is when we try to get a good amount of computing power from edge tech like mobile phones, they obviously are inferior when you compare them to proper servers which have a lot more GPUs to handle the AI workloads. But if we want to design hardware that can also work in an endpoint like a mobile phone, then we have to reduce the amount of power usage, right? Because there's a difference between editing an image where you want to fill in a certain region with AI, where you edit this image and you get the output, but your battery or your charge percentage is dropped by 15, right? With just one image. But using these specialized AI accelerators, which are very good at managing power, you can maybe drop it to just 0.5 percentage per image. So that's a very significant increase, right? In a practical use case, I wouldn't want to edit an image for 15% of my battery life. I would rather just do it for 0.5, right? So using a GPU, using my inbuilt GPU, I can accomplish that task of editing the image with that 15% example. But using an AI accelerator that's specially modified for my phone, I could do that same task with that 0.5% example. So that's why edge tech in AI accelerators is very preferred now. And moreover, we also need to make sure that the software also supports the streamlined workflow of this accelerator, because usually workflows are they're bottlenecked by the scheduling algorithms and the memory management algorithms as well. Because nowadays it's no longer dependent purely on the math or the methods that we apply mathematically, but it's also dependent on the memory management. So we have a few papers that we've observed being released in this year in 2025, where they're mainly focusing on managing this memory, this time that's wasted on memory. So you have two blocks, right? You have all the registers or the processing elements, and then you have a memory block here separately. And the problem with these operations or the existing methods was that the results of certain computations were stored in the memory, right? So you have to compute with this core, and you have to fetch the memory and then give the memory result back to another processing element, right? But what they've done is they've managed to remove this memory step to a certain extent and make sure that the results are going back and forth between different processing elements as well. So because of that, the memory utilization is decreased and the processor utilization or the accelerator utilization is increased. So it's gone up from I guess 60 to about 89, which is very significant, because the main goal of these AI accelerators, like we've discussed, is to reduce the power consumption and also preferably improve performance, right? So this will improve your efficiency, and because of that, that will increase your performance in a certain way as well. So you're not going to use that much power, because accessing memory is also going to take a lot of power. And you can also make sure that instead of having these many processing elements and using only 3 people in the bus, we can also ensure that, like in this example, instead of dropping our processing element utilization by jumping to memory blocks, we'd rather keep the utilization high by using inter-element communication. So that's related to how in a bus we have 15 as our maximum capacity, and we're using, let's say, 10 or something over here in this 60% example, and we can bump it up to 13 or 14 in this 89% example. So because of that, we're not wasting any resources that we have. And scheduling algorithms, in a way, we can make it more efficient, because in case we have 4 elements that can do the processing, and we have, let's say, 100% workload, right? So if the 100% workload is given to this first core, let's say core, and the rest 3 are going to remain stationary or idle, right? So we're only having a 25% utilization. What we can do is we can just split all the work into 25. So instead of one block handling everything or one core handling everything, we'll just split it to all the different cores or the different processing elements. And that's one way that we can also improve efficiency in an accelerator as well. There's also a lot of other papers that talk about flexible scaling. Since we've said that matrix operations are very important for AI workloads, we're going to have a linear path, right, in these accelerators that follow a proper assembly line related structure, right? So what we often come across is certain matrix operations will have, let's say, dense or sparse matrices, right? So that will drop efficiency because sometimes you're going to have to skip through a lot of zeros, and that will take time. And due to that reason, we create different algorithms that can change the assembly line limits or the bandwidths, so that instead of processing every matrix in a uniform manner using a bus, we can make sure that the sparse matrices use, let's say, a smaller car, and the dense matrices use a bus, because that's a bit more efficient, right? So that way we can make these linear systolic arrays a bit more efficient as well. A systolic array is basically this chain of operations that every AI accelerator is supposed to do, and they're also the reason that they're very really quick and efficient, right? So I think we've looked at why AI accelerators in the big picture are very important for edge computing of AI tasks as well. And I think we've understood that it's very important to form AI solutions that are bounded with proper limits, so that we don't waste resources from CPUs or GPUs. Rather, we build these accelerators that are just enough for the task. So if our task is, let's say, this much of a percentage or volume, our AI accelerators shouldn't be this much, as in they shouldn't occupy this much space, right? We could easily create a module that could handle this much of AI workloads, but we only use this much. But what we'll rather do is we'll just create hardware that's supported by software that can handle this much of a workload. So in case there's any case of overhead or leaks, we can also manage it. So it's important to make it not so tightly wound, but also pretty relaxed as well to handle, like I said, any leaks as well. So I think that's it about AI accelerators, and I hope that you guys understood everything in a very conceptual manner, and how these processing element blocks work, and how the memory blocks work as well, and why it's important to implement inter-element communication rather than just referencing memory every once in a while for computations. And yeah, that's about it, and I hope you guys understood it very intuitively as well. And yeah, keep learning. Curiosity is the only reason we've gotten this far, and I'll see you guys in the next one.